Now, what is the per unit system? Well, it's a method that is largely used by mechanical engineers. I guess that there are some mechanical engineers here, right? No? So essentially, you don't want to represent quantities like current voltages, power flows, admittances, impedances, using their original measurement unit, amperes, volts, watts, volt amperes, ohms, Siemens, but you want to adimensionalize them. So you want to have adimensional measurement units. Why the per unit method is very interesting? Well, I don't know whether you pay attention to that, but electrical circuits are characterized by parameters, by quantities that are varying of several orders of magnitudes. I don't know whether you pay attention to this. It's a very unique properties in our universe. For instance, the electrical resistance. Okay, into a conductive material, the resistance can be in the range of, if you take copper, for instance, you are in the range of 10 to the minus 8 ohms per meter. If you take an insulator, it's 10 to the plus 9. Okay, so essentially you have a quantity that can vary of tens of order of magnitudes. Even in a power grid, you can have flows or injections which are in the range of gigawatt, so 10 to the plus 9, and current flows which are in the range of amps. So you have quantities which are moving of several order of magnitudes. Now, when we put together these numbers into a numerical solver, we are using computers, and computers, they don't have an infinite precision. Huh? So playing with numbers that have very, let's say, that have differences in amplitudes of different order of magnitudes is not good. So in order to solve this problem and have all the quantities that are moving between 0 to 1, let's say they are close to 1 in general, we use the per unit value method. So what is the per unit system? So essentially, the per unit system is obtained when all the quantities of your physical system are divided by what we call base values. Okay? So let's suppose that you have a generic quantity is indicated with the A upper bar, so it's a complex number, so real plus J imaginary part. So the per unit value of this quantity normally is indicated using a non-capital letter, so the A non-capital upper bar is equal to A capital letter upper bar divided by AB. So AB is the reference or base value used for this quantity. Let's make an example. Let's suppose that you have a power plant, a nuclear power plant, that has a rated power of 1 gigawatt. Okay? So AB is equal to 1 gigawatt. Okay? So this means that all the injections of this power plant in per unit are ranging from 0 to 1. Okay? That's the concept. It's just this. So essentially, this division by the base value is valid for the complex quantities, but also for the modules of the complex value. So if you write the complex value of A in per unit as a real squared plus imaginary squared, and then you transform them by using the base values, you see that is equal to the module of the original complex number divided by AB. Now, in order to make the per unit value to be coherent, is not sufficient that you choose A, B as you like. For instance, in electrical systems, we have voltages, currents, power, impedances, admittances. Can I choose the base values for these quantities as I want? The reply is no, because in order to have a coherent system of base quantities, you have to respect, to guarantee, the same links that are existing between these quantities in the electrical grid. What I mean with that? Now, let's suppose that you have three quantities, A, B, and C. And these quantities are linked together by a constraint, which is, for instance, C equal to A over B. You can choose only two base values. It's up to you which ones. For instance, I choose AB and CB and BB as base values. The value to be used as a base for C is not free. Is equal to AB divided by BB. If you do that, you create a coherent set of base values. Okay. How many degree of freedom you have in a power grid? Did you ask your question yourself? How many degree of freedom you have in a power grid? If we go back, you remember the two-port equivalence? I mean, I can go back myself. Let's take a very simple example, of a two-port equivalence, okay? Like this one. How many degree of freedom you have? How many variables you have? 4. 2 voltages and 2 currents in the 2 ports. How many constraints you have? How many equations you have? These are the constraints. 2. How many degree of freedom you have? 2. Okay? So this means that when you are creating a set of coherent base values for a power grid, okay? So you have the freedom of choosing 2 base values, okay? So in power systems, we need to set the base values for power, voltages, currents, impedances, or admittances. So it's a system that has 2 degrees of freedom. Normally, in power grids, we select the base power, AB, and the base voltage. Why we do that? Well, because the voltages in the system are more or less constant in all the nodes. Okay, this is for guaranteeing the insulation of the system. So typically, the base voltage of the system is the rated voltage of the grid in that particular part of the grid. Okay, and the base power is typically the AB is selected as the power of the largest machine of your system. Okay, so this means that the injections of powers, they are all spanning between 0 to 1. For instance, you have the largest power plant of the system. I don't know, it's 2 gigawatt, 3 gigawatt, I don't know what it is. AB is the base power of this machine. All the other quantities, IB, for instance, is derived. It's just AB divided by VB. The ZB is VB over IB, so VB squared divided by AB. So the base impedance and base admittance and base currents are just derived from the base quantities of power and voltage. Okay, so in all the exercises that we are going to do, we are going to use the per unit value. We don't use the values in watts, ohm, amperes, volts, etc. We always use this kind of stuff. In three-phase systems, again, you have to make a little adaptation. You again choose the base power AB and the base voltage VB. The base voltage in this case is the can be is the phase-to-phase voltage. So the IB is just AB divided by square root of 3 VB. This is just because of the relationship of the three-phase system. Okay, and the EB, which is the base value for the phase-to-ground voltage, is VB divided by square root of 3. Now, why electricians, and in particular power systems people, they do like the per unit method? Because it has a very unique property. And this unique property is related to the treatment of the transformers. But before looking at this aspect, just to make this very simple exercise. So I have a grid of 3 nodes, 1, 2, and 3. So there are 3 lines of 50, 100, and 100 kilometers. So these are the parameters of the lines. R prime, X prime, G prime, and B prime are the longitudinal resistance, longitudinal reactance, and the G is the shunt resistance, is 0, and the B prime is the shunt capacitance. Okay? The line is rated voltage is 220 kV, and the base power is 100 megawatts, which is assumed to be the largest plant connected to these 3 nodes. So calculate the admittance matrix in per unit. It's very easy. So I compute the base power, PB is 100 megawatt, VB is 220 kilovolts. The R prime, this is the per unit longitudinal impedance of my lines. Per unit of length is just equal to R prime times AB over VB squared. And these were ohms per kilometer. These are now per unit per kilometer. Okay? The same thing I do for X prime and for B prime. So these are adimensional values per kilometer for the resistance, reactance, longitudinal resistance, longitudinal reactance, and shunt capacitance. Okay? Now, how can I build the admittance matrix? So the Y12 is just equal to 1 over 50 kilometers times R prime plus J X prime. So this is just because of this. Okay. This is the longitudinal Y between 1 and 2. Same story is for the Y13, sorry, is 1 over 100 kilometers times R prime plus J X prime, because again, I have one line connecting 1 to 3, and the same thing is for the Y23, which is 1 over 100 kilometers times R prime plus J X prime. So these are the elements of the, pardon me, these are the longitudinal elements of the admittance matrix, or the branch admittance matrices. The shunt admittances are very easy, because in 1, 0, so in the node 1, who is incident, who is coming in? The line of 50 kilometers and the line of 100 kilometers. Right? Both these lines are incident in the node 1. So the Y10 is equal to half. I remind you, half is because the shunt is split in 2 half, one in the 1 and one in the other node. 50 plus 100 times JB prime. Okay? Same thing for the Y20, because in the node 2 I have incident a line of 50 and the line of 100. And in the node 3, I have incident a line of 100, another line of 100. Okay? Did you understand why I have the half here? Yeah, because the pi, for those of you that didn't pay attention, we are using equivalent models of the branches, yeah, which are pi. Okay, so the shunt, the total shunt, is split at half in one node and the other half in the other node. Okay, that's why I have 1 over 2. So let me go forward. Okay, so I have all the branch admittances, all the shunt admittances. Yeah, and these are the computation of the admittance matrix. So the Y capital letter 1 is equal to Y non-capital 1 2 plus Y non-capital 1 3 plus Y non-capital 1 0, because of the topology of the system. Y22 and Y33, same story. These are the diagonal elements of the admittance matrix, and these are the off-diagonal elements of the admittance matrix. This is it. Okay. So as I was saying before, why electricians, let's say power systems guys, they do like the per unit method. As I was saying before, they do like the per unit method because it simplifies a lot the circuit where there are transformers. Now, to show you this, I'm taking the equivalent circuit of a transformer and I'm transforming it in per unit. So I know that there are some of you that are not very familiar with the equivalent circuit of a transformer. So essentially, a transformer is a machine, this is for the non-double E guys, okay? which is transforming the parameters of the power. Okay, so you have, it's a two-port system, it's like a line. Okay, the only difference is that in this port you have voltage E1, current I1. In the other port you have current I2, port voltage E2, and the ratio between, let's say, the transformer is a machine that can manipulate E1 and E2 by orders of magnitude, by using a magnetic coupling done by windings, essentially. Okay, I can have E1 in the range of 380 kilovolts and E2 equal to 20 kilovolts. Okay, so the machine is built in a way that the flows of power is kept almost constant. Okay, so if I manipulate the amplitude of the voltages, since the power flow is constant, I have to manipulate also the values of the currents. So essentially, if I'm stepping up the voltage, I'm stepping down the current, and vice versa. Okay, so this is the equivalent circuit of the machine. It's composed by an ideal transformer. So this is a transformer which is stepping up E1 to E2 by a factor of n, and is stepping down the current from by a factor of n. Okay. In series with the ideal transformer, I have a longitudinal short circuit impedance, ZSC, which is a characteristic of the machine. I can measure it. And a shunt magnetization admittance, Y0. Again, I can measure it. Okay? So this is for a real machine. Now, let's write the two-port. Can I represent this by a two-port system? Yes. So let's write the equations. E1, I can just apply Kirchhoff. So E1, so this is the voltage at this port, is equal to the voltage here, E1 prime. Now E1 prime is equal to N E2, okay, times the voltage drop on ZSC. So plus ZSC times I1 prime, but I1 prime is equal to N to I2 divided by N. Okay. So this is how I derive this equation. So it's Kirchhoff to the loop composed by here E1 and E1 prime. Okay. Then I can write also the second equation, which is the Kirchhoff law applied to this node. Okay. How can I write Kirchhoff to this node? Well, it's pretty straightforward. It's equal to I1 is equal to YI0 times E1 plus I1 prime. Okay. Now I have I1 is equal to, maybe I can use the board because it's a little bit easier. So this equation is equal to I1 is equal to Y0 times E1 plus the current which is flowing, let's say the I1 prime. Okay, but this can be written as Y0 times E1, I have it, so is equal to N E2 plus ZSC over N times E2 plus I2, I1 prime, I can write it as I2 divided by N. By refactorizing this, I get this equation. Okay, so this is how I get these two equations, which are linking E1, I1. So this is essentially the voltage and current in the port 1 times E2, I2. E2 and I2 are the voltage and current in the other port. It's like a line. It's like a two-port. Okay? Is passive? Yes. Is reciprocal? Yes. So it has all the properties that we have seen till now. It's not a line, it's a transformer. Now, if I choose two base voltages, VB1 and VB2, to be the primary and secondary rated values of the transformer, such that their ratio is equal to n, where n is the transformer ratio. So I choose the base values for the voltages here and here, such that the ratio is equal to n. If you write the two equations in per unit, they become like this. And interesting enough, this equivalent circuit is equal to a shunt element, a shunt admittance, and a longitudinal impedance. Here there is nothing. Magically, the ideal transformer disappeared. And this I can treat in series with other lines and other branches because I don't have the transformer any longer in the circuit. That's why we like the per unit method, because we make disappearing the transformer in the electrical circuit. Okay, that's the interesting aspect of using the per unit method for the transformers. Okay. If VB1 and VB2, they don't have a ratio equal to n, well, you can still use a pi circuit. The only thing is that the pi circuit becomes a function of m, where m is the new ratio, m is equal to n times the ratio inverted of the two base values that you're going to choose. You can still apply the theory, but you're complexifying a little bit the pi circuit of the transformer. Okay, but the interesting thing is you can still treat the transformer as a pi circuit, which is finally the hypothesis that we made to build the admittance matrix. Okay. Good.